Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
So by testing the thermal conductivity, we have huge optimizations of our whole system because we can now dimension according to true and accurate in situ thermal conductivities and do not have to make overly conservative assumptions on the thermal conductivity of the soils. And that has enabled us to dimension cable spacings in an economical way that is much more reduced than the sort of standard practices.
That's just a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant atmosphere continuum. Today's guests are Kai-Julian Hendler and Christoph Verschaffel-Drefke. Kai is a geotechnical consulting engineer at Boley Geotechnik in Munich, Germany. He holds a master's degree in civil engineering with a specialization in geotechnical engineering from the University of Lisbon. Previous to working at Boley Geotechnik, he was a site engineer on port construction projects in South Africa, Guinea, and Australia. In his current role, he focuses on the geotechnical challenges of infrastructure projects for railways, metros, roads, and underground cables. Christoph is a geotechnical engineering and hydrology coordinator for Transnet BW, a transmission systems operator in Germany. After getting his degree in geoscience engineering, he worked on several research projects based around the heat dissipation of underground cables. During his 6 years working at Transnet BW, he has overseen projects relating to thermal soil investigation, thermal dimensioning, bedding materials of cables, and heat emissions. And today they're here to talk about their work at the intersection of geotechnical engineering and soil thermal characterization, which led to the development of one of METER's newest instruments. So, thank you again, both Kai and Christoph, for being here with us.
Thank you, Brad. Excited to be here.
All right. So today we definitely wanted to talk about a few of your projects and research interests. But first, can you tell us a little bit about your background, how you became interested in the sciences in general and arrived at your specialties within geotechnical engineering, thermal design, etc.? We'll start with you, Kai-Julian.
I started off actually studying mechanical engineering, funnily enough. And in my first year of mechanical engineering, I kind of realized in a couple of months that I'm not that passionate about engines and cars, for example, and sort of realized probably it's not the right type of engineering for me then. Pushed me to go into civil engineering, which has always got that strong geographical background, and eventually into geotechnical engineering, which has also got that not only the geography but also the geological aspects, which has always fascinated me, and that aspect of interacting with the sort of structures, grounds, how that works, and ultimately, getting involved in civil engineering to sort of satisfy, I guess, my job need and contribute to society in some sort of way. So, now finally, over the last couple of years, got involved through Boley Geotechnik. We were involved in one of the major underground cable projects, Südlink, and that's how I started getting involved on thermal conductivity of soils and this whole topic that we're going to talk about today.
Great. Christoph, how about you?
The story starts a long time ago. So at the end of my diploma, I developed some measuring devices or methods to determine hydraulic parameters as well as thermal parameters, to combine measurement methods of thermal and hydraulic parameters on one soil sample. And I tested that in the lab, and one of them was the method to combine an evaporation test with a thermal needle. This I have done in the background of geothermal engineering, but I asked me, is that relevant for the geothermal field? Because the water movements around soil heat exchangers is not so relevant for the modeling of soil heat exchangers in the geothermal field by the low thermal gradients of these exchangers to the soil. Buried cables have much higher thermal gradients, have more problems with moisture movements around these cables, and therefore we look for some projects to improve the thermal design of buried cables. Yeah, and that was the starting point of my PhD. I get some industry project with different German distribution grid providers. In this case, I've built up in this project test site for buried cables, with real buried cables, which are used commonly in the distribution grid, as well as I conduct some lab tests as well as some bigger lab tests for investigation of the drying out phenomena around cables from one of our partners, E.ON Bayernwerk, and is in the soil investigation in the Bavarian area with a lot of soil samples to investigate the hydraulic and thermal properties of these. And we see, there's a big potential for an optimization because the state of the art dimensioning of cables consider a fully dry out of the soil above the groundwater level. And we see from measured parameters of the soil and our physical model of this drying out processes, we have seen, normal conditions of such a cable, we haven't any fully dry out. We always, so in not coarse soil, so we only have a certain reduction of the water content and therefore much higher thermal conductivity also in the close vicinity of the cable. As well, we see from the soil measurement itself the usually used assumption of the thermal properties of the soil. The most of our soils have much higher thermal conductivities, and there's a big potential by a thermal soil investigation for a better efficient dimensioning of these cables. That was also the reason why I've looked for the SouthLink project. It's a more than 700 kilometer transmission line project. And therefore, since 2019, I worked for Transnet BW to optimize the dimensioning of these cables. As well, we have implemented a soil investigation, a thermal soil investigation along the whole route of this cable.
So both of you have mentioned the SouthLink project. Can you give us a kind of a quick background of that project, its significance for Germany's energy transition? Germany has some pretty high targets and initiatives to achieve those targets of being basically net zero emissions, et cetera, and developing some green infrastructure. Can you talk a little bit at kind of a higher level, give us some background of the SouthLink project?
Sure. As you mentioned, Germany does have very high targets for reducing their carbon emissions, I think like many countries nowadays as well. One of those targets, I believe, is to reduce their carbon emissions from pre-industrial levels by 80% by the year 2030, if I'm not mistaken, and then become totally carbon neutral by around mid-century. And obviously, a big part of that means to develop the renewable energies, which are not centralized as sort of fossil fuel energies like coal-fired power plants and others. So in Germany's case, you have a lot of renewable energies, specifically wind energy in the northern part of the country, some onshore, some offshore as well. And you also have more solar power, sort of photovoltaic energy in the southern parts of the country. And you have also a lot of industry located in the southern parts of the country in Bavaria and another state called Baden-Württemberg. Basically, because of this decentralized power which is being created in the north, that energy needs to come to the south. And that's essentially what SouthLink aims to do. And this, the underground power line, I think Christoph mentioned it earlier, is 700 kilometers long in total. So it starts off just north of Hamburg and then runs down from pretty much the middle of the country to the southern states, Bavaria and Baden-Württemberg, and ends a bit north of a city called Stuttgart. So that's the main aim, is obviously to be able to transport this renewable energy and do that in an efficient way by using direct current power cables. That's why this project is also a very integral part of the energy transition, because it's going to enable the renewable energies and the wind energy produced in the north of the country to be used in the south, where it's specifically needed with a lot of industry, as well as being able to transport some of the solar energy from the south to the north.
The project undergoes some restrictions which we don't have in the past. So as Kai said, the length of the project is only one of them, but also the power of the cable with 2 times gigawatt transmission capacity. This leads to cable dimensions, which are new for this voltage level. We have some restrictions that thicker cables can't get produced and developed by the manufacturers in the expected project time. So we are restricted to a 3000 square millimeter copper cable. And this leads to the need of thermal optimizations. Usually in the transmission grid, there's not the problem, because if you have any thermal problem, you choose a thicker cable. Okay, thicker cable also is more expensive, but as we see now from the SARSLink project, it is a secure way to do soil investigation for this economic design of cable roads.
I was going to ask along with that, I don't know if you are privy to all of the discussions, but how did the choice come about to develop and begin to use buried cables, underground cables, as opposed to overhead ones?
This is a political decision. SouthLink previously was planned as an overhead line. And I think it's around about 2012, much public resistance. There was a political decision to give buried cables priority. And therefore, SouthLink was stop the planning and redo everything new as a underground buried line.
All right, that makes sense. We see that here in the States as well and elsewhere. Especially if this is a nationwide project, there's a lot of stakeholders, a lot of people where you do need to find that balance and compromise in many ways often.
Absolutely. Christoph, do you know how many stakeholders there are? I just know that Südlink crosses thousands, if not tens of thousands of different properties. So yeah, you can imagine the stakeholder involvement that's involved with that project.
In practice, how does an engineering firm like Boley Geotechnik and a transmission system operator like Transnet BV, how does that collaboration begin, and what does it look like?
Yeah, as I started in the project, there always was a collaboration with Boley Geotechnik for geotechnic stuff. So I think in the past, Boley has done some geotechnical reports for Transnet BW. And it becomes clear very early that we have to do soil investigation, thermal soil investigation, and we need a lot of manpower to develop the whole new process of the thermal design of power lines. So because state of the art was to take very conservative assumption of the soil properties, and now the new way was to take measurements and make dimensionings based on this measurements.
There's whole new processes that were basically developed as part of the Südlink project, and these processes needed to become a bit formalized, structured, so that they could be applied on a large scale by all the different design offices involved, because obviously every section of the project, there are many different sections on the project, and each section is being designed by a different design office. So that's why all these new processes had to become streamlined, optimized, and I think a transition had to be made from the research aspect to the industry, where a lot of the research could be applied. And I think coming back to your original question, Brad, maybe just to add on to what Christoph already said, is that obviously because it's an underground power line over 700 kilometers, everything that's underground is going to have geotechnical questions and will need to be considered from a geotechnical aspect, which is why for us as a geotechnical consulting company, that it was obviously a perfect match, I would say. We obviously have that experience with planning ground investigations, assessing the soil parameters, defining these soil parameters on various other projects that we've been involved in, also on large scale projects, although Südlink is probably one of the largest ones. And for that reason, I think, as Christoph said, a lot of manpower was needed, which is why that collaboration with Boley and Transnet and the other transmission system operators was needed. Then just basically to develop besides all the standard geotechnical investigations and ground investigations that happened, a new aspect was this investigating the thermal conductivity of soils.
Yeah, so there's no project before in which we have thermal ground investigation in this amount, and therefore we have to write down a lot of specifications. In the first years, we make a lot of research for questions. For example, how dry can a soil be in our region under natural conditions without cable? And the second question, how dry can a cable be, and what's the impact on the thermal conductivity when the cable is under power? And also some questions, how can we reduce the amount of bedding material for cables? So we have developed a lot of concepts which are now going into practice for recycling the excavated soil and recycle it as a bedding material and all of these stuff. So we have to manage all these studies and take the results together and make company standards from that. So that's the reason I also one of these standard was a standard for the Southlink project, how to measure thermal conductivities of soils. And this standard now is reworked to a standard which was agreed between all 4 transmission grid operators of Germany. And at the moment, this method is also going into a standardization of the German standardization organization.
For those in our audience who are neither soil scientists or geotechnical engineers, can you give us a brief overview? You've talked about soil thermal conductivity and others. Can you give us a brief overview of what soil thermal conductivity is, why it's a critical parameter in this project, in cable design, in all of this?
Basically, when electrical energy passes through a conductor, such as a cable, some of that energy gets converted to heat energy, right? And essentially the cable heats up. And what we have with SuitLink, there are a total of 4 cables that are laid underground at various spaces to each other. And obviously these cables will heat up and they can also heat each other up. So what needs to happen is that the heat generated by these cables needs to be dissipated through the surrounding medium, which in this case is soils, and needs to be dissipated efficiently so that you can ensure that the maximum operating temperature of the cables doesn't get exceeded, as this would obviously impact the efficiency of the whole cable system and reduce its capacity to transmit energy. That is basically why it's so important to know what the thermal conductivity of the surrounding soils is, so that you can dimension these cables and make sure that you have your cables spaced far enough apart from each other. But obviously you also don't want to just space them too far apart and make extremely conservative assumptions, because then it just becomes uneconomical, and obviously the environmental impact becomes bigger because you have more impact on the environment by digging up more ground. So yeah, that's why thermal conductivity needs to be investigated, and soils are such a varying, as you probably know, and yeah, many listeners I'm sure as well, soils are such a anisotropic material, so they vary so much in their properties given on location, depth. There's so many aspects, which means that thermal conductivity is also a highly variable parameter of soils, as it's not only dependent on, for example, the soil density, but also on the water content of the soils and the type of soil as well, like the grain size distribution. That's why it's so important to test the thermal conductivity, essentially to be able to make sure that you can dimension your cable spacing properly, or also the backfill materials, so-called bedding materials, that is basically the ground that comes in directly around the cables.
Just for clarification's sake, are the cables buried directly within the soil, or are they within some kind of piping or tubing?
It's a good question. So you have 2 construction methods, basically. You'll have either an open excavation, where the cables are buried at a depth ranging between about 1.5 meters to typically more or less 3 meters. And then you'll also have trenchless construction, which is when you need to cross any infrastructure like railway, a road, a river, or other sort of natural obstacles. And the trenchless construction is done typically via HDD, which means horizontal directional drilling. or also through microtunneling in some special cases, and also a very big tunnel in one special case, where the Elbe River is being crossed in the northern Germany. And to get back to your question, it depends on the construction method typically. Well, for the first installation is a sort of ducting, casing tube, I guess, made of HDPE. Then the cables are laid inside of that. And for the open excavations, this depends on the site. There, the cables are basically installed directly or also installed into casing tubes.
Kai, you mentioned backfilling as well. And so I've got a couple questions regarding that. There's a wide range of variability when it comes to the soils that you're working with, but also when it comes to backfilling as well. I mean, for lack of a better term, you do want the cables to be able to quote unquote breathe, so that there's less issues of overheating, which is one of the reasons why we're working with the soil thermal conductivity there in those soils. Do you expect that the fill material there around those cables, will it stay moist? Is it going to be drying out? Is there going to be some expectation that it will remain at a stable thermal conductivity?
So maybe the quick answer is no. But depends on, of course, so many factors. We've basically, within the project, we consider this a steady state where we generally look at what happens on the worst case. But in reality, what happens is that you have precipitation, you have rainfall, maybe snow in some regions. That water will obviously infiltrate, and that will change the water content of the bedding materials throughout the seasons, throughout the year. Of course, even maybe a bigger influencing factor, you have groundwater fluctuations. So your groundwater can vary also throughout the year or throughout different dry and wet season spells over multiple years. So basically all of these environmental aspects will influence the water content within the bedding materials and in the soil generally around the cable. So obviously if you have a very low water content in general and your cable is actually buried quite close to the surface, then the water content may not change as much, but I guess the closer you are to the groundwater table, probably higher fluctuations will be experienced.
Is one of the goals for these bedding materials, is it to replace the native soil, or is it to have separate fill material? And how does compaction, when the bedding materials or the soil is then compacted back to its original state? Do you prefer using fine or coarse materials? How are things planned out there for that?
One aspect that we should definitely mention is that in the open excavations, the cable spacing has a constant distance between each other. So as opposed to the trenchless constructions, crossings, where the cable spacing varies, the open excavations, typically the cable spacing is standard at about 1.9 meters, so roughly 2 meters. Which means that in order to keep the cable spacing constant, if we need to be able to adjust another parameter in those zones, which is the thermal conductivity of the surrounding medium. Now, the in situ soil we can influence to a certain extent, but if that thermal conductivity of the in situ soil is not good enough, then one does need to bring in basically imported material, and that has a higher thermal conductivity so that you can have better heat dissipation and thereby still guarantee that 2 meter spacing.
Also, the mechanical properties are also relevant for the decision if we need some special bedding material. So, because at some points we have a really high stone content in the soil, and it's not possible to recompact the excavated soil back to its initial state, as well as for protection of our tube, or in the northern part for the direct laid cable. If we lay a cable directly in the bedding without a duct, so there are very high restrictions on the maximum grain size. There is also only rounded grains allowed, and not any sharp edges in the bedding material, and therefore there is a special bedding material needed. There's no possibility to reuse the excavated soil.
From my understanding, the Südlich project is taking place kind of, I don't want to say, I guess piecemeal, at least in different parts in different places simultaneously. How flexible are your plans or your designs? Is it something where you can modify your designs based on what you're learning from your thermal conductivity testing, whether in that same place or elsewhere?
That has been quite a challenge actually on this project, because a lot of the design phases have been running concurrently in order to try and speed up the project in total, which means that while the ground investigation was still running, which means the thermal conductivity results were still coming in, certain assumptions were made, I guess, on cable spacing, for example, and designs, which then had to be verified again at a later stage to ensure that the cable spacing and the thermal design really meets the actual requirements. There are definitely very different parameters that you can still adjust in order to maybe try and meet or optimize your design. One of them would be, for example, in closed crossings, to put a thermally conductive material such as water into the casing pipes, and that obviously improves the general thermal conductivity around the zone of the cable. Other measures would be perhaps to change the layout of the construction. There are also other sort of service fiber optic cables that are also being constructed at the same time. One can switch positions with these and the HVDC cables. Possibly in some cases where it's really required, you can also reduce the construction tolerance, but that obviously is not an ideal solution, as that's something that you're increasing risks in later down during the construction phase. And for the open excavations, I could say one is probably more flexible because you are still able to adapt your requirements and adapt the bedding material that you can install.
Is the temperature then being continually monitored with these buried cables?
Inside the conductor, there are some fiber optic cables to measure temperature and also vibrations. As well, we have some additional of these cables in the close area to the cable in some extra protection pipes. So we are able, when the fiber optics going blind and we are not able, maybe in 20 years, the fiber optics can't be used. We are able to also use the second fiber optics, or in this tube, we can change the fiber optics anytime.
Let's dig into methodologies then as we're moving along, especially as a research instrumentation company here at Meter. We're definitely interested in your methodologies, in what instrumentation you're using, how you're going about sampling the soil, what you're doing in the field versus in the lab. So if you could give us just kind of a quick overview of the sampling that is happening before the excavation is being done, if there's any that's during, and then also after the fact as well. What all goes into that process?
The majority of the thermal conductivity testing that we did was during the ground investigation phase. And basically there we retrieved soil samples from on site, from the boreholes, or also from excavation pits. Ideally, undisturbed soil sample will typically give you the best results because it does the structure of the sample. The soil structure is way more intact than, for example, a disturbed soil sample, obviously, which means that typically your thermal conductivity results will also be more reliable. However, that's not always possible. It can be quite complicated, which is why we did also do a lot of testing on undisturbed soil samples. I think the whole methodology that was developed in this project, and also, of course, using the equipment, thermal needle probe, and the whole setup developed by Meter Group, was ideal for this whole setup because it allowed you the flexibility to use both disturbed, undisturbed samples. We could adjust the densities that we installed the disturbed samples in, make a judgment there on I guess that was the engineering judgment that needed to be made, unless there was specific data available on what the required density is to install the sample. And then there were a whole bunch of specifications that we developed on how the samples need to be transported, how much time they need to be kept, reserve samples, what temperatures the tests need to be carried out on, how the water saturation happens. That was obviously also a huge aspect. There's so many small details that one needs to consider in order to get a reliable, reproducible, and accurate test result.
So that's the reason why we have to write down the whole process as a specification. There are, on the market, there are only some standards which are describing only the sensor, the thermal needle. and not the whole process of collecting soils, put it in the lab conditions, and how to saturate and so on of soil samples, and how to pack samples as well.
Yeah, some of the more details from the sampling, specifically with the needle probe, is only actually suited for relatively small grain size. So once you have a lot of gravel content in your sample, that makes the insertion of the needle probe much more difficult, which means that was one aspect that we had to develop in this project, how to deal with that, because the gravel content is quite important actually for the thermal conductivity, as the gravel is made up of small rock fragments essentially, which are nice and dense, which means that they have a higher thermal conductivity compared to, for example, your sand or your silt, whatever, where this gravel is in, which means that we still had to develop ways to keep that, to consider that and quantify that's beneficial effect from the thermal conductivity of this gravel, but also allow for it to be extracted in order to be able to perform the test with the needle probe. I think another aspect was the packing, how the packing needed to happen in the sample cylinders, the dimensions of the sample cylinders, how that we could dimension these large enough to avoid sort of boundary condition interference during the test, but obviously you still had to make it practical, economical essentially. So that was another aspect that needed to be considered. And of course, we had really great experiences with Meter Group in Munich in Germany. In the laboratory in Meter Group, we had very close interaction with your colleagues there in Germany, and could go there at any time, see how where problems arise, when we had some teething issues, we could go there, identify these, and really optimize the whole process. Basically led us to be able to do more than 6,000 tests, 6,000 thermal conductivity tests. So really a huge amount of testing that was done. Those little aspects and steps got defined into this industry norm that Christoph mentioned, and is now currently being worked up into a national standard.
And talking about that interaction with Meter Group there in Munich, Christoph, my sources tell me that you were instrumental in instigating the development of our new Varios instrument, which provides automated thermal dryout curves and other things. Can you talk a little bit about that experience in working with the development of that instrument?
So I never used the Various device itself. So in the past, I used the Hyprop device, and added a thermal needle probe, and therefore, I think the Various will be a great development, because you have both integrated in one device, in one software solution. The Various will be a great development of this device, because you have both possibilities in one device to measure the hydraulic properties as well, the unsaturated hydraulic properties, as well as thermal properties in one device on one sample. And there you don't have any complications to fit a measurement of you have done on one sample of the hydraulic properties and another sample of the thermal properties. You collect it at the same time, and you're safe. Both measurement fits together, and it's also cost efficient, because you have only one device in which you can measure everything together.
Kai, you mentioned over 6,000 samples that have been taken, which is a huge number, and I'm sure that is continuing to grow as the project goes on. Do you foresee, I guess, any ways where the work that's being done in the lab? So you mentioned all the I don't want to say problems or issues, but everything that needs to go into being able to take the sample, package it like you said, keep it stable, send it back to the lab, take those lab samples, work on them there, and then find the results there. Do you foresee any way that either a need or a way that the quote unquote lab work can be done out in the field?
Yeah, I think it's possible to set up a container in the field. Of course, it might be a bit more difficult to get stringent laboratory conditions if you want to dry out your soil sample at a constant lab temperature. Obviously, a container might be more susceptible to other interferences if it's being shared with other laboratory activity. But I think in theory, it's definitely possible that one could set up a mobile lab. Why not? probably has some certain advantages because you reduce the transport of the sample, which reduce, at least for undisturbed samples, that'll reduce the risk of it getting damaged or loosened, and might also make it much simpler to execute these tests and reduce some of the logistical steps required to sending a sample a couple of 100 kilometers away into a laboratory.
I guess on the flip side of that as well, do you feel that as you've been using the tempos, the thermal needle, has that provided you enough information in doing those spot tests with those thermal probes where that might be good enough as opposed to sending samples back to the lab?
One of the aspects which is why we did the lab test, or the lab tests were preferred in this instance, at least for this application, is that the thermal conductivity of a soil, as I mentioned earlier, is very highly dependent on the water content. And for soils that are in close proximity to cables, the water content varies a lot depending on the proximity to the cable. So if you have, let's say, for example, you have a cable buried in sand that is above groundwater level, the sand that is close to the cable will be much drier than the sand that is at a further distance to the cable. Which is why when we test the sand, we want to test the entire relationship of water content to thermal conductivity to see what is the thermal conductivity of the sand in its saturated state all the way down to its oven dried state. And there were certain water balance models that were developed as part of the project where we could estimate then and say, right, we know typically for sands at this depth, et cetera, it'll naturally dry out only to sort of X percent. And we know then that'll be the thermal conductivity of the soil in the far away from the cable, and the thermal conductivity of the soil close to the cable, which is basically almost oven dried, or at least with very, very low water content, will be the one. And you need these two thermal conductivity values in order to do your thermal design and dimension your cable accordingly.
And it's when you when you make a spot test in the field, you only measure the thermal conductivity at the state the soil is. So you measure the different thermal conductivity maybe in the end of summer than in January, for example.
Has there been any redundancy in the tests that you've done? I guess, kind of a blind test and sending some to one lab and sending them to others.
At the beginning of the project, we have a second contractor, second lab in which we have done this measurements. There we have some measurements which we can compare, but there are some issues with the quality of the data format which we have which we get from the other lab. So as the project progresses, so we only work with Meta Group.
I did have another question as you were talking, Kai. In the future, after the cables have been buried, is there going to be, if not continuous, is there going to be monitoring in the field of the thermal properties there as you go along? So over the next however many years, I don't want to say set it and forget it, but is there going to be field monitoring of the buried cables after the fact?
The cables will be monitored exactly with the fiber optic cables. So the underground copper cables, power cables will be monitored with using the fiber optics. The actual soil properties along the route and specifically the thermal soil properties, as far as I know, they won't be monitored because at that point it doesn't really help you much. So you'll probably, I don't think we're going to be measuring the thermal properties of the soils. I don't know, Christoph, maybe you can add more onto that.
So we make the dimensioning on the worst case which we can happen on this point. So we from our soil investigation, we have the whole TC water content curve. For the dimensioning, we take the worst case natural water content and the worst case natural thermal conductivity of the soil, the driest natural state of the soil, and the highest dry out point of the soil, which can happen by the cable at this point. These two parameters we take into account for the thermal dimensioning, so we are safe. There's no need to have a look on the actual state of the soil or or water content of the soil.
So basically, it's a matter of making sure that everything is 100% ready to go once it gets buried. So all your readings are good. You know the properties of the soils and of the bedding materials, and you kind of and you can work from there. Are there any, I guess, any strategies that you use to identify and mitigate what you would call maybe hot spots in the sections of the line? So where the soil, thermal conductivity is highly variable from the surrounding area.
In the early design phases, they do a clustering, not us, but other project participants have done thermal clustering of the soils, which also helps the designers to choose the routes and identify the best option of where to plan the routes, so that we can avoid these areas with very poor thermal conductivities, the thermal design much harder. I think that's probably the main aspect.
The thermal clustering was done by a university or collaboration with the university, and they have used all map material and drilling information which we get from public information we can get of the soils, and from this information they used a lot of pedotransfer models to make assumption of the thermal properties of the soils. These leads to maps, to geoinformatical systems maps with thermal conductivity layers. They make interpolations in the horizontal and vertical direction, and therefore we have some planning for the early planning state.
With all of these, I guess all the readings that you've taken, all of the tests that you've run in the samples, has there been, you talked about thermal clustering, which is interesting. Have there been any other findings that have stood out to you? And again, you're working across almost the entire length of Germany, but has there been anything else that has stood out to you in your findings?
Perhaps one aspect which sort of stood out was that when doing the design, developing a thermal ground model helped a lot, as that just helped you visualize the problem. And effectively, a thermal ground model is using the results of the thermal conductivity tests and putting these into your geological section. So your cable runs along a certain route, passes these different geological layers, and then try and allocate each geological layer, or even within a layer, you could separate those to sub-layers and sort of allocate them certain thermal classes. This sort of thermal model was a tool that really proved indispensable, and to really understand a problem, and also just a good design practice to follow, as it enabled one to maybe look back at a design during the construction phase. If problems were encountered or certain challenges were encountered, one could look back at the thermal design and say, okay, this is what was done, this is what happened. This is why we now can accept some sort of deviation, or can't, and need to find a different solution. I think that was very interesting.
Kai, earlier in the discussion, you had mentioned also working on standards with regard to soil thermal properties. Can you go into a little bit more detail about that process, about how you're developing standards, what that process looks like, and what the final outcomes might be?
Maybe I'll go back a couple of steps, which we might have mentioned this before already, but the processes for testing the thermal conductivity as we're doing it now, the whole process from sampling, packing the sample, saturating the sample, inserting the needle probe, the size of the sample, performing this continuous measurement, doing the final drying in an exsicator, and also doing the weighing in order to determine the water content, is really a whole process that was developed in the Südlink. And we started off a couple of years ago where a project specification was developed, which all geotechnical engineers on the project and the laboratory meter group actually had to follow. This policy, or the specification, was adopted obviously by Transnet and Tenet, which are two of the four transmission system operators in Germany, as they're involved in the project Südlink. But the other transmission system operators were possibly doing not quite the same process, as obviously these transmission lines, you interact with many different operators, and typically projects get developed jointly. Very quickly, I think the need arose to have a unified, standardized approach on how to test the thermal conductivity, as it was clear that it's such an essential aspect of the thermal design. And if we don't have something that's standardized, it's very difficult to just claim thermal conductivity result if you can't explain the exact process that you did it in, and you need to be able to compare apples with apples. Quickly, the need arose to standardize this approach across Germany, at least, which is why the various members of the transmission system operators got together and then worked out the nitty-gritty details, what the process is that needs to be followed so that everybody's happy with that, and also allow for different preferences, I guess. This need was also identified by the German Institute of Standardization, so DIN. And towards the end of last year, we started working together with them to basically use this industry norm, which we had developed, and adapt that to become a German national standard. Worked with them at the end of last year, had to do, of course, a bit of editing to meet their requirements. And currently now this norm is being processed, and the draft will be published soon, hopefully, to be open for public comment. Unfortunately, only in German at this point. Hopefully, it won't take too long to get it into English so that it can be also more internationally recognized. But yeah, so at the moment, that's the stage that we're in. That draft needs to be published and then become open for public comment and public feedback. And then once it passes that stage, then it can hopefully go into the final publication and become an official standard.
So with everything that you've done here with this SuedLink project, are there any findings or, as you talked about, standards and practices and processes, anything that you have discovered or that has worked well for you that you feel will be applicable to other projects dealing with underground cables, other projects that are in Germany or the rest of Europe or worldwide? Anything along those lines? Anything that you feel that, yes, we can contribute to these new projects that might be going on in the future?
Primarily, this whole testing methodology of testing thermal conductivity is just proven itself in this project. As we mentioned earlier, the unique aspect of this is that you've got now a reproducible methodology where you get the continuous measurement of the thermal conductivity over the entire water content range, which is very useful. The whole methodology that we have has a high degree of automation, thanks also, of course, to the equipment that Meter Group has developed, but it has a very high degree of automation. It's reproducible. We do have a high degree of accuracy. We tested the samples on reference samples, such as certain ceramics and gels, which means that this methodology is not only reliable, but also really scalable and economical, which means it can be used on a large scale, and has already been adopted by the 4 German transmission system operators, as we mentioned earlier. And I think a point that Christoph already mentioned briefly earlier was that this is actually, of course, the most important aspect, is that doing the thermal conductivity, we have huge optimizations. Sorry, by testing the thermal conductivity, we have huge optimizations of our whole system, because we can now dimension according to true and accurate in situ thermal conductivities and do not have to make overly conservative assumptions on the thermal conductivity of the soils. And that has enabled us to dimension cable spacings in an economical way that is much more reduced than the sort of standard practices up until now. And of course, it has also reduced greatly the need for bedding materials, at least most of the times. In some cases, of course, you might discover that you have a very bad soil and then need to compensate for that as well, which is also good because it means that we can design and dimension the cable routes more reliably, more effectively, so that it can operate at a high efficiency over its lifetime.
Do you see the role of geotechnical engineering, I guess, evolving as we hopefully transition more to renewable energy systems like the one that SuedLink supports?
I think geotechnical engineering has to evolve and has to keep up with the times. Of course, this aspect has been probably proof of that. As for your average geotechnical engineer, you don't really have much interaction with this aspect of thermal conductivity of soils, but not only for underground cables is this applicable. Thermal conductivity of soils is also very relevant for the dimensioning of heat exchangers, ground source heat pumps, and those sort of aspects, which does play its role in the energy transition as a sustainable or renewable energy. that definitely will be an aspect. This whole energy transition is obviously pushing new technologies onto a bigger scale. And as an engineer, and definitely as a geotechnical engineer, we'll have to adapt to that and embrace it, of course, and look at the exciting new opportunities that are coming.
Along with that, do you see any emerging technologies that, such as like advanced sensors or machine learning models, other things like that, that will be able to help optimize, thermal management of these underground cables or engineering, these large scale infrastructure projects?
Mentioning AI now, of course, that's definitely also an aspect for us as geotechnical engineers, which is always becoming more and more relevant. We deal with huge amounts of data. I mean, as one can see on this example of this, more than 6,000 thermal conductivity tests that we did as part of the Zootlink project. And in order to evaluate this data, help us do better predictions in the future, perhaps, or just evaluate the data to better understand patterns and trends. I think artificial intelligence, machine learning will start playing a more significant role at a very, very rapid rate. But which is also good though, because it does enable you to really evaluate that data and takes away some of the grinding work, gives you some interesting, or can give you some interesting results. One always does have to be careful though.
All right. I think our time is up for us today. Thanks again, Kai and Christoph. Again, we really appreciate you guys being on and talking with us. It's been a super interesting conversation.
Thanks, Brad. Yeah, really appreciate it for the invite, and really enjoyed it. So thanks a lot to you too, and to your colleagues as well.
And if you in the audience have any questions about this topic or want to hear more, feel free to contact us at metergroup.com or reach out to us on X at meter_ENV. And you can also view the full transcript from today in the podcast description. That's all for now. Stay safe, and we'll catch you next time on We Measure the World.